W.
W, right? W. Because only with respect to weak operator topology we have compactness. Of course, you can consider a strong operator topology. It will be even not only a semi-topological semigroup, but even topological, but you lose compactness. You know. So, with respect to weak operator topologies, we proved it. For every reflexive space, it is a compact semi-topological semigroup. So, it's very nice characterization. It means that closed subsemigroups of such special, relatively special compact semigroups cover all possibilities of abstractly defined compact semi-topological semigroup. The proof is expected. I think we can skip it because we use L2 sum, some large, this time some large L2 sum, and this proof will guarantee whenever we have sufficiently many functions and you consider some big reflexive space, and then you obtain, after L2 sum of representations, you get some naturally defined cohomomorphism which will be embedded, because in each you have sufficiently many. This means that you can separate points and closed subsets, and so everything is quite expected and natural. But a central idea and central tool is the main theory. Of course, the rest is expected. Okay, the fact I already mentioned, speaking about L4, if you remember, there's some general characterization of representability of groups. That the topological group is reflexive representable if and only if weakly almost periodic functions separate the points and closed subsets. You can ask, but here in the first condition something different. First of all, I should explain, because I used several notation before. It is almost the same, but anyway, let me explain. Here I write G for simplicity GW, but I mean GWAP. I already used it. What was GWAP? It was Gelfand space of G, or compactification of G, which comes from just algebra of equivalence periodic functions. Gelfand space of G, and it gives universal semi-topological semigroup compactification of G. We already discussed this point. Universal means that for every other possible morphism into compact semi-topological semigroup and its compactification, we have an unique way to extend it. But as a warning, of course, this map by no way is not necessarily embedding, and it might be even point for infinite groups. One of the results I mentioned at least 2 times as a warning that for G H plus 0, 1, it happens that this map, so U, let's say U, some universal. Our U in this case just collapses to 1 point. It will be 1.7. It's 1 point. It's trivial. And in other language, it means by our theories, of course, by everything controlled by this algebra, that every weakly almost periodic function must be constant. Constants always are always constant. Weakly almost periodic, you notice constants is nothing, it's invariant functions. So as small as possible. So another way to write it is that weakly almost periodic G is just all possible constants on G. Not else, nothing else. Okay, so that is why by this description of U, first condition is the same as by saying that your weakly almost periodic functions separate points and closed subsets in order to get embedding back to this one. Okay, I started from this, wanted to explain this point. So again, so I say here embedding, and meaning it is equivalent that weakly almost periodic functions separate points and closed subsets. It's the same.
I have a question. The compactification with respect to
yeah?
Yes. Is it some general theorem that the compactification?
Absolutely.
No, I mean, is it somehow general that the compactification has on itself the right group structure, or
this one?
yes?
Yes.
Because
as I think historically it comes from the Liu-Glixberg classical works, and anyway it was the most systematic way. They proved it in their paper, and it's quite standard that this algebra as corresponding compactification is some categorical object with this nice universal property.
But it does not have to happen always that the compactification will have the group structure.
What open?
That the compactification with respect to another subalgebra of CG,
Yes.
it does not have to contain the group structure, or does it?
No.
No.
No. So it is very typical that, no, we already discussed this point. If you need here group structure, that is the significance of Ellis theorem you mentioned. If you need, okay, it's a good point to ask some such question, because if you need to remain something from group to group, it was very no. But it is impossible because it is, we have the criteria. It happens if and only if you get here just a Bohr compactification. So what's the case? Almost periodic functions are the same as weakly almost periodic functions. If what you wish, if you wish to remain to get here again a group, but by Ellis theorem, semi-topological group and topological group are the same. You remember? We already proved it during the first lecture. One of the points why Ellis theorem is so popular, your question, of course, very natural. That's the the question is important. So that is why Ellis theorem, not a unique reason, but one of the reasons why it's an important point. So the question is not, and we know any time when you have weakly almost periodic larger than almost periodic, it is not true. In a natural way, I mean. Extending natural.
Is it maybe...
By the way, Ellis theorem is here. The next application.
Is it related to the fact that on, say, beta n you don't have group structure, but you have semi-group?
Delta Z, for example.
Beta z.
No, delta Z is even a much worse case because you lose even semi-topologicality. So we have only right side, the continuity. You definitely have a semi-group structure. It's good, compactness of course. But you have only right continuity. But what is interesting, it is for many cases it is enough, and it reflects the fact that such animals are envelopic semigroups of something. And there are many, this theory is quite good, even for even the general position of such compactifications are just right topological semigroup compactification and not topology. For example, I already mentioned that for these nice Polish groups, we have nothing here. We have just one point. Okay. Now, so by the way, continuing with your question, why it happens is the point is compact group, you can see, but what happens here? After weakly almost periodic is just constants, almost periodic are the same. So in this case, weakly almost periodic are the same. So is the same. So it is was quite natural what we get here. Sketch of the proof of okay. Here we have Ellis-Lawson joint continuity theorem. We have very quick proof using the geometric ideal representations. One of the influential theorem is Ellis-Lawson joint continuity theorem. This theorem is a generalization of Ellis theorem, and it looks something like topological, but it has many applications. And one of the applications is just much more general than Ellis theorem. So what is Ellis-Lawson's continuity theorem? If you have some subgroup in compact semi-topological monoid, then and suppose that we have separately continuous action on some compact space. Then the action, restricted action on your group, on your subgroup, will be jointly continuous. And in this situation, moreover, G is a topological group. G is a topological group we already proved, even if you remember, in our proof of Ellis theorem. But what about Ellis-Lawson joint continuity theorem? We can mimic this situation, embedding this situation into some reflexive space. I mean, we can reduce the proof, the question, to the particular case, very particular case of some dynamical systems which we many times used before. I mean, in this case, consider our action of G on X. And this action will be weakly almost periodic, because if you consider it comes as a restriction of compact semi-topological semigroup. So if you consider the closure of G, it will be something semigroup. The closure of G will be semigroup, right? In semi-topological semigroup. The closure of sub-semigroup will be again semi-topological semigroup. So what we get here in this way, it is easy to understand that, for example, by Grothendieck's lemma, that every function will be weakly almost periodic, because every orbit of function, say fg, you can get as the orbit of the corresponding closure. But corresponding closure is some compact semigroup, semi-topological, and its image will be compact. And you get pointwise compact subset which is bounded. And what we said about Grothendieck's theorem. This theorem says that bounded pointwise compact subset into C of x, where x is compact, this will be automatically weakly compact. It's a non-trivial part of Grothendieck theorem. So we get a weakly almost periodic system. And if it is weakly almost periodic system, we can apply our machinery of the Davis-Figel-Johnson-Brzezinski based theorem, and we have approximation by this kind of dynamics. I mean this kind of dynamics, which are canonical dynamical system associated to every Banach space, in this case to reflexive Banach space. So our question can be reduced to this particular case after this approximation. And in this particular case, we have in a very good position to use something we said before, because if you consider theta of V acting on our V star, our V is reflexive, yeah? Again, we can use the fact that, so G is here. If G is here, I mean the image of G will be of course into isometry group, right? But into isometry group, we have the privilege to apply the coincidence of weak operator and strong operator topology. So remember, we proved it during the first lecture. After V is reflexive, we know that weak and strong are the same on this part, isometries. So this does not matter, all or not. In particular, we can look at G on image of G as embedded into isometries, and whenever it does not matter weak or strong, we can use strong. And with respect to strong operator topology, we already know that even if we have some semi-group and consider strong operator topology, the corresponding action is jointly continuous. Here, at this point, if you take a weak, here weak star as usual, we have separate continuity. But when you consider, let me recall, we also proved it, if you take a thought, then this action, big star, is jointly continuous. So that is why, after we know that G or image of G, everything can be determined by the image, as the H, our G is here. We have H of G, and it is here. Then, as we can consider a strong operator topology by this argument, so we automatically have the continuity. The point is quite clear. Okay, so as a corollary, we get the compact semi-topological group is a topological group. You remember that argument because, again, you can see it immediately. Because if G, the image of G will be topological group, okay? Because HG here is a part, again, maybe I missed to say, but remember, here is the key idea is here. HG into isometry part, in the isometry part, the two topologies are the same, and we have sufficiently many H's of this kind, and finally, G embedded into product of images. And product of topological groups is topological group, so everything becomes straightforward. Okay, now some parallel hierarchies and later some examples, some continuation of So that's those list of examples. In order to understand what is the main idea, you should recall what was the definition of what we had the Megrelishvili, but we had also functions like Asplund functions and the Tane functions, right? So our strategy now is to extend or to mimic the original theorem or case of reflexive case, to extend it for Rosenthal and Asplund spaces. And we already felt, I think, what is the machinery of the main theorem. Again, Davis-Figi and Johnson-Penchinsky, but we need to check some technical moments. In Asplund and Rosenthal, these moments are much more serious, besides some continuity problems I mentioned. But I think better to skip these technical parts. It is quite difficult to understand because I still need to understand in my investigation some points. So I can imagine that for you to understand it's quite long. So let's concentrate on some applications. And what is good is what we can do. Everything in this file is self-contained. At least I tried to write everything in a way that almost everything is, should be understood or self-contained, or at least with some links to references. So interested people can understand the rest, but let's give now some overview, because the main idea of my lectures was not some particular individual results, but to see some hierarchies and sometimes some parallel hierarchies. So first of all, let's formulate a theorem. So the title is small families. So what is general idea? If you have some family of functions on your topological space, or in most cases for us compact space, then you need to understand when your setting can be represented, or again, the same question, but now for in general situation. And again, bounded. But now we need to understand when we can be, say, Asplund, or when we can be Rosenthal. And for F, the name of the game, the key idea was what? Double limit property, or reflexive. Reflexive is already done. Here, reflexive. Central idea was F has double limit property, or it's the same, the closure, pointwise closure, is still consists of continuous functions. So it was the first case. The second case, we need to understand what happens. We need now to represent our family on some Asplund space. And by characterization of Asplund spaces in terms of fragmentability, quite expected to try to mimic the situation. So anyway, you need to extend it, to put it into Asplund space. So in a Asplund case, your F, what kind of combinatorial or some other restrictions are you looking for? So in this case, F will be there are some equivalent possibilities. fragmented family, or equifragmented, as I said, on X, it is equivalent that the closure also, pointwise closure is also fragmented family. Moreover, if our X compactor is metrizable, it is equivalent, by the way, that this is metrizable. It's a very nice characterization. I will continue, I will explain it tomorrow. And the third, what is that idea of smallness, where we need V to be Rosenthal, and F will be eventually fragmented. Eventually fragmented, I already mentioned in my definition, it is equivalent, eventual fragmentability, that the closure, pointwise closure, consists of fragmentable functions on X. I mentioned that the idea of this equivalence comes from Dallegran work, and in fact by Dallegran, Bourget, Fremling-Dallegran results, very well-known results, and this characterization is very far from being easy, but at least on the level of formulation, it seems quite natural. I wanted here to present some kind of parallel here, and we continue this explanation, these ideas tomorrow. It's the time to finish today, and thank you for your attention.
Thank you very much. So we meet tomorrow 10:15. There is a short break.